Throughout this quarter, we've seen several different types of reactions that produce gas. And the problem with gas-producing reactions, whether it's sodium bicarbonate in acid, magnesium metal in acid, or zinc metal in acid, is if you want to do any stoichiometric analysis, you need some way to capture the gas. In each of these reactions, as the gas is being produced, since it's just open to the environment, it completely leaves the container, and we have no idea how much gas is produced in order to do our stoichiometric analysis. So we get some specialized glassware. This is referred to as an eudometer. You can't quite see it well because it is a very long piece of glassware. It's very similar to a burette, except instead of having one opening and a valve, it's got one opening and one closed end. So we can make a setup that effectively will capture the gas and give us a measurement of how much gas is produced. And that's what we're going to do today. So here's how it's going to work. We're going to have our eudometer with some amount of hydrochloric acid in the bottom. I'm using blue dye as an example in this case. And what we have to do is we have to get this whole setup flipped over, and we want to use the water pressure inside this beaker in order to make it so all of our material stays inside. Now, because of the water pressure, right, this column has a particular width and there's a certain amount of pressure from the water here. There's essentially going to be some balance of the pressure of the water down and the atmospheric pressure of the water in the beaker. Still, because of the density differences between our acid, or in this case our blue dye, and water, you can see the blue dye will slowly start to make its way down. And eventually it'll hit our reactive surface. There's no reactive surface in this case, but this is to demonstrate two important things. Important thing number one, there's going to be some water pressure associated with this system as well. If this column, if the eudometer was much taller, the pressure of the water in this column would actually be enough to overcome the atmospheric pressure. So this is a particular height with a particular width in order to make sure that the atmospheric pressure and the water column pressure balance each other. So we're going to have to be thinking about how the pressures play against each other in this reaction, or in the amount of gas we produce. And also, I just think this looks really neat. The process of the material kind of tumbling down, mixing. And as an example, we can just go ahead and imagine, well, if I remove that atmospheric pressure of water, of course, an air bubble will make its way inside. And now we can look at this and we can hypothetically think about what gas is in the top of my eudometer. So up here, we've got some amount of just air, right? So that's going to have some nitrogen, some oxygen, carbon dioxide, and water vapor. It could also have some amount of whatever material is in here that could be becoming a gas as well. So in addition to thinking about the water pressure, and now we've got some gas pressure in the top as well, this is going to be exerting some pressure in addition to the water exerting pressure against our atmospheric pressure. We can also think about how each different gas inside of here exerts some pressure. Since the atmosphere is 70% nitrogen, the pressure of the gas is going to be 70% due to nitrogen. And there's going to be that nice kind of relationship of the amount of gas is going to be related to the pressure it exerts, as long as we're dealing with an ideal gas. So let's go ahead and get our setup for our reaction. Okay, so we're just about at the end of the reaction. That took about 15 minutes. We can see we still have a little bit of magnesium reacting there at the bottom, so we'll let it keep going, but while it's going, we're going to talk about some of the concepts here. So, at this point, we have our gas collected in the eudiometer. Further. Okay, good enough. So, up here we've got our gas collected with the reaction between magnesium metal and hydrochloric acid. This is predominantly going to be hydrogen gas. It's not going to be perfectly hydrogen gas because we've got water contact, and I also had a slight little teeny air bubble at the top when we started. But when we start thinking about this, we can use the eudiometer to measure the volume of gas produced. We'll let it finish reacting before we actually measure it, but it's already at about almost exactly 79 milliliters of gas produced. So we can very easily measure the volume of gas using this closed piece of glassware. The thing that's a little bit more challenging to measure is the pressure in here because of those things we were talking about earlier. In addition to the pressure exerted by the gas, we have the pressure exerted by the liquid water. And we can actually figure out how much pressure is exerted by the liquid by measuring how the height difference, right? Because this is a gravitational effect, water pushing down. So if we figure out how high over the beaker water surface our column water is, we can use an equation to figure out our gas volume. Sorry, our pressure from the water. And that is at almost exactly 16 milliliters. Sorry, 16 centimeters for the water height. I'm writing all of this down so we can do some consideration. And then our volume of gas produced, it's like 79.02 milliliters of gas produced. So at this point, we can start to think about how we use the ideal gas law in order to relate our ideal stoichiometry to our actual yield. And to do that, we're going to go to the whiteboard. So in our experiment, we could very easily measure the volume of the gas that was produced. And we have numbers for that. We had a volume of 79.02 milliliters. We can very easily measure the room temperature, which was 23.1 degrees Celsius. We can figure out the pressure. This one's a little bit interesting for our experiment. The room pressure was approximately 1 atmosphere of pressure. And what we have to do is we have to figure out not what the room pressure was, but we have to figure out the pressure due to the gas we're interested in, right? This N, this number of moles of gas, this ideal gas law is for that one gas that we're looking at. So if we want to figure out the moles of one particular gas, we need to know the pressure associated with that one particular gas. So the pressure is going to be a little bit tricky. We're going to need some equation to get the pressure. The number of moles is also an interesting thing here. We can use our stoichiometry to figure out how many moles we should have produced. And we can use that number of moles to then say, okay, this is the volume or the pressure that we should have got if everything was behaving ideally and if everything worked out perfectly. And then R, the ideal gas constant, perfect reaction. And then the ideal gas constant, we could treat this as an unknown to solve for, or we can just grab it off of the periodic table. I like the old version of this lab where you're supposed to calculate the ideal gas constant. Also, you have to be careful with the ideal gas constant. Don't get it confused with the Rydberg constant. And also, where is it? There it is. You also have to be very careful about the units of the ideal gas constant. Liters, atmospheres, moles, Kelvin. Right, so when we're looking at this equation is kind of the reason why it's really important to go to Kelvin in terms of the units we use. If we rewrite this equation as PV over RT equals N, what happens at 0 Celsius? All messes up, right? 0 Celsius would make this an undefined expression. So going to Kelvin, where you don't cross 0, you don't have negative temperatures, you've got some absolute 0, and all temperatures are greater than that, Kelvin is going to be the best unit to use in that case. And this is kind of the reason why we switched to Kelvin. Now we're going to solve this in two different ways. Notice we've got liters. Atmospheres is a really nice kind of unit. It's really just looking at, if you're on the surface of Earth on a pretty average day, you're under about 1 atmosphere of pressure. There's just the pressure of the air above you pushing down on you is about 1 atmosphere. Very human scale relevant. Now what we're going to do is we're going to do a couple different things. First, we're going to say, well, let's do an ideal calculation and say, hey, what happens if I use these numbers and what volume of gas should I produce, or what pressure of gas let's do what pressure of gas should I get. And we'll compare that to what pressure of gas we actually get. So first, let's show that it's not just that we're not at exactly 1 atmosphere of pressure. So what we're going to do is assume 1 atm. So we're going to assume that we have 1 atmosphere of pressure and all gas is the H2 that we made. So in this case, the pressure is 1. The volume is what we're going to solve for. We've got a measured volume, and we're going to compare our calculated volume to our measured volume. Our number of moles we have to calculate, ideal gas constant is 0.08206, and the temperature is going to be, I got to do 2 calculations. So the first calculation we have to do is how many moles of gas did we produce? We'll do the easy one first. 23.1 degrees Celsius plus 273.15. It's going to give us our Kelvin. And I can almost do this in my head. 306.25 Kelvin? Let's see, 7, 8, 9. Nope. Math is hard. $296. Because 2 and 7 is 9. Yeah, 296 Kelvin. Notice we dropped the degree when we're going to Kelvin. And that's because Celsius and Fahrenheit is all a relative scale. And Kelvin is set off of the absolute zero. So it's not a relative scale. It's just Kelvin. We've got to figure out how much gas we made. So I've got magnesium metal plus HCl. It's going to go to magnesium chloride plus H2 gas. Balanced. from the setup we used, we know that this is excess. And this is limiting. This was 10 milliliters of 6 molar HCl, so pretty concentrated HCl, even though we didn't use very much of it. And our magnesium was 0.074 grams. We can calculate the grams into moles. And get 0.00304 moles magnesium. Since magnesium is the limiting reactant, and because there's a 1-to-1 mole ratio between the moles of magnesium and the moles of H2 produced, we can pretty easily multiply by the 1 mole H2 for every 1 mole magnesium, and that's going to get us 0.00304 moles H2. We can go ahead and plug this moles of H2 and this temperature in Kelvin back in. So we're going to have, ooh, I didn't give myself enough space. 0.00304 for our moles, 0.08206 for our ideal gas constant, and 296.25 for our Kelvin. The nice thing is, since we assumed 1 atmosphere of pressure, we can easily divide that over. We should have units here for everything. We're going to have the moles cancel, we're going to have the Kelvin cancel, we're going to have the liters cancel, or sorry, we're going to have the atmospheres cancel. We should just be left with a volume. So if we had an ideal reaction at ideal conditions, we would have made 73.9 milliliters of gas. And you look at it, we made 79 milliliters of gas. So from this, you can clearly tell, experimentally, we made more gas than is theoretically possible. Isn't that great? Well, no. So whenever we get this, if we did a percent yield calculation of this, we would find that our percent yield is over 100%. And whenever you get a percent yield over 100%, it means you've got contamination. Well, not always, but usually means you've got some contamination. We are counting something as hydrogen gas that's not actually hydrogen gas. And this is going to come from 2 sources. One, our pressure is not 1 atmosphere. Some of the pressure is actually due to our water column, so we've got to correct that. And 2, not all of this volume, not all of the volume is from hydrogen gas alone. There's also going to be some water vapor in there. So there's 2 corrections we have to do in order to fix this calculation, and you can see how to do those corrections from the background of the lab. In the background, we can find a couple equations. The first thing to focus on is this equation at the top. Ignore these for a moment. So the calculation we just did says that the pressure of the atmosphere is equal to the hydrogen gas there. This is ignoring the fact that there was that liquid left at the bottom, so there's some pressure due to the liquid. So we can add that term in and say the pressure of the atmosphere is the hydrogen gas plus the H2O liquid. And then we can also say, oh, there's also some water gas because that column had water in there. There's going to be some just at room temperature. There's going to be some water vapor in that space with the hydrogen gas. So we can also say, hey, there's going to be some H2O gas in there as well. When we subtract these off, we're going to see that the pressure of the hydrogen gas is actually going to be less because these two things shouldn't be counted as hydrogen gas. To get the H2O liquid, we have this first equation. This is essentially an equation, we just get it from the background. This is particular to the eudometer we were using. That's where this 13.6 millimeters of H2O comes from. The eudometer has a particular circumference, a diameter associated with it that gives rise to this equation to relate the pressure of the liquid to the height of the liquid to the pressure. And then we can also say that the pressure of the H2O gas is going to depend on the temperature of the liquid. So we've got this equation where we've got temperature modifying the pressure that we're going to feel, the pressure that's going to be exerted by the water vapor. And we can go ahead and calculate both of those and figure out what our proper pressure is. So we're going to get something that's going to be like solving for pressure of hydrogen gas. We're going to get pressure of the atmosphere minus the pressure of the H2O liquid minus the pressure of the H2O gas. We can go ahead remembering that this temperature is, of course, in Kelvin, so that's going to be 296. We can go ahead and calculate this from our previous values. As a reminder, it was 16 centimeters, which is 160 millimeters. So the pressure due to the H2O liquid in atmospheres, that's what that last bit there is for, 0.01547 atmospheres. And then due to the H2O liquid, this will take me a moment longer. I have to do it step by step because I'm messing up in my calculator. And I've made a typo someplace. Oh. So I just did the calculation and I got 40 atmospheres of pressure. That is because I forgot it's 0.0 there, which means this is going to be 382. Okay, that's going to make more sense. Okay, whew. Back to calculating. You can notice both of these corrections are relatively small, but that they're not 0. 0.025 plus. So our pressure due to H2 gas is going to be reduced to 0.9595 atmospheres. Now that is the pressure inside that space due to just the hydrogen gas. And now we can repeat our calculation with this pressure of hydrogen gas to figure out how much we should produce. So we can think about this in terms of a second calculation. Rather than getting our moles for a perfect reaction, we can say, well, how many moles of gas did we actually produce? Solving for n in this case, we know the volume, we know the pressure, we know the ideal gas constant. We can solve for that number of moles, and then we can figure out what our percent yield is and see if it's still above 1 or if it's below 1. I'm going to guess real quick that it's still going to be above 1, just slightly, or sorry, above 100%, just slightly, because I did have an air bubble in there, which is going to contribute additional volume that we haven't taken into account anywhere. But let's go ahead and see what we get. Pressure is 0.9595. 0.9595. Volume needs to be in liters. That's going to be 0.07902. N is the thing we're solving for to compare to the number of moles that we had in our ideal case. Ideal gas constant is 0.08206. And the temperature is 296.15. So in this case, we can solve for our N that we actually obtained experimentally, rather than just doing the stoichiometry and saying, oh, we're going to make all the gas. What do we actually get? We can calculate a number of moles here of 0.00311 moles H2. So in this situation, you can see that we still end up with a number of moles slightly greater than our perfect stoichiometry, probably because of that air bubble I had at the top of the tube, some experimental error. If we were doing this for some publication or just, being experimentally correct, we'd repeat this experiment 2 to 30 more times and then take averages of everything, and we should get something that's pretty close to 100% yield. The point of what we did just now was to show how we can use the stoichiometry to predict a volume of gas produced and then do a comparison and say, oh, there's some experimental versus theoretical difference. Or we can use the volume of gas we collected to say, oh, how much gas does that correspond to? Doing some of the corrections that are necessary, correcting our pressure rather than having perfect atmospheric pressure, saying, oh, we also have to take out the fact that there's some water pressure from the liquid and there's some water pressure from the vapor to get us close to an ideal reaction. What I really like about this experiment is it shows you how you can do some problem solving and take what we theoretically do on paper, which is always just, perfect conditions, and we can get something and say, oh, we can start to think about the things that are happening in the real world and how we can get closer to the correct answer, a better representation of what's happening in the real world, which is really the entire point of chemistry.